Okay, you should have out your notes for lecture 12. And I'm going to begin by just looking at this little data set here. Let me just actually put it up. It is the numbers 2, 5, 6, 9, 12, 2, 5, 6, 9, 12, 13, 17, 20. Okay, first question, find P30. So why don't you pause me and see if you can do that based on what you learned last time. All right, I'm going to do it now. There are 1, 2, 3, 4, 5, 6, 7, 8 data points. So I take the percent here, which is 30% or 0.3, times the number of data points, and I get 2.4, and I round that up to 3. So I go to the third data point. There it is. So P sub 30 is 6. Please try to find P sub 35. All right, so pause me again and see what you come up with. All right, I get 0.35 times the number of data points is 2.8. And that rounds to 3. So 1, 2, 3, it's still 6. So P sub 30 is 6. P sub 35 is 6. So 6 is the 30th percentile. It's also the 35th percentile. What's going on? Well, it's not that hard to see. I say here, what's going on? It's not that hard to see that really the problem is we have so few data points. It's a small data set, right? It's such a small set, 8 numbers, you probably wouldn't want to do much statistical analysis on a data set that has only 8 data points in it, right? It's not like you're going to gain much by doing a lot of analysis. It has so few data points that to jump from one point to the next, I didn't say it, but I already have them in order, right? You have to have them in order to do these calculations and get the right number. So if they're in order from smallest to largest, to jump from one point from the next means you jump over a lot of percentage value, right? Let me just say it like that. Jump over, or you have a large change in percentage of the data set to your left. Right? Each time you take a jump, you're getting a big chunk, a big percentage change in the amount of data. Okay, so of course, what that means is that there's a lot of, so to speak, percentage in between those data points. And so it shouldn't be surprising that the same data point can have a lot of different percentages, percentiles associated with it. Okay, so you're getting a large change in percentage with a small data set. It's not so much the case when you have a large data set. So with large data sets, each point, I'm using the non-technical word, each jump to the next point is a small change in what percentage of the data you have now to your left that's less than you. So each jump to the next point is a small change in percentage. So different percentiles usually are represented by different points. So different percentiles are usually represented by different points. And you don't have this sort of a thing going on so much. Okay, I wanted to point that out just because we learn how to compute these things, but we should be able to think about them a little more logically and kind of understand what's going on. And I say down below here that it'd be nice if we could have a very simple view of the data along the number line. Actually making use of percentiles is what I want to do here. And one way to do this is with what's called the 5-number summary. I think I can fit that in right here. Let me change color. Definition. The 5-number summary consists of or comprises of a data set. Well, 5 numbers. The first number is the lowest data value. Okay, and then actually the top number, the 5th number that we'll have here, will be the highest data value. If you recall, the difference between the lowest and the highest is what we call the range. And this is giving me the total spread of the data. If I know the lowest value and the highest value, I know the total spread. But I'd like some kind of an indication of how the data are spread in between there. They might not be spread evenly across, right? And we can get that with adding in, well, a good number to add in, I'll put it right in the middle because that'll be it, will be the median. Okay, this will give us the middle value of the data points. And what I want to do is get a number in between the lowest value in the median. So the median, really, this is the 50th percentile, right? I don't know if I've said that explicitly, but that should be clear that we're looking for that point that is 50% of the data to its left. We're looking for that middle point. The next point here is the so-called first quartile, which I will say it's Q1 is its symbol, and that really means just the 25th percentile, okay? So parenthetically, I say that's just saying the 25th percentile, but the term we use is Q1, and this is, like I said, it's called the first quartile. Okay, well, P50 or the median is sometimes called the second quartile, almost never. We just call it the median, and we jump over here for the next one, which will be halfway between the median and the highest value, essentially, Q3, and that's, not surprisingly, the 75th percentile, right? So this is the third quartile. All right, if we can find these 5 numbers, it's just 5 numbers, and it can give us kind of a good idea of how the data are spread along the number line. In fact, it leads, if you see the next page, it leads to something that we're going to call the box plot, or the box and whisker diagram, which you may have already heard of. And I put down there that it'll be best to define that in the context of actually working a problem. We're going to use the 5-number summary, and the box plot will give us kind of a visual image of that. All right, so if you read what I say there, in this example, I consider this rather large data set, large by what we've been doing. It has 180 points in it. That's not really that large if you're analyzing data in the real world, but it's it's big enough to kind of illustrate our purposes, and it's also not so big that it'd go on for pages and pages here. All right, and I say here I actually randomly generated numbers between 0 and 15. I just used Microsoft Excel to generate these numbers. So if you think of this as a data set, it could represent, we went out and captured 180 sparrows and weighed them, or we captured 180 crickets and measured how long they were, or whatever. Right? We got out and got this set of numbers. Don't want to take the time to go do all that, so I just had Excel generate some random numbers between 0 and 15, and I had to go out to the nearest hundredth. All right, so we have this data set. Boom, that's what we get. And I say before we go any further, of course, this is a data set. We could get a nice summary of this data set by doing a relative frequency diagram and a relative frequency histogram. And probably we wouldn't want to have a bar over each individual value. We'd want to have our classes be intervals of values, right? And so I asked there, well, what should the class width be? And I asked this just to kind of, think if we were going to use techniques we've already learned, what would we do with this data set? Well, I tell you, it goes from 0 to 15, roughly. So you might think if you want 10 bars, you'd want a class width of maybe 1.5, right? If you did that, you'd start at 0 for your left endpoint. You start at 0, and then to go to your right endpoint for the first interval, you wouldn't go up to 1.5, right? You would go to 1.5 Well, since this goes out to the hundreds, you go out to 1.49, and the next one would be 1.5 to 2.4, I guess 2.99, right, et cetera, et cetera, et cetera, and just add the class width. So we could do that here. Or we might want to use class widths of size 3.0 to get 5 bars instead of the 10 bars. But we're not going to do that. We're going to do something totally different. Instead, we're going to do this 5-number summary. So what I then did is I had Excel order these from smallest to largest, and that's the data set you have on page 3 there. It's the same data set, just organized from smallest to largest. And it was easiest to have Excel go smallest, the next smallest, the next smallest down columns, and just go across like that instead of like this. So if you look at that data set, excuse me, you'll see that it increases along columns. All right, so why don't you stop me and do the 5-number summary. So you're going to find the smallest and the largest. That's easiest. Then you've got to find Q1, the median, and Q3. And you have to remember how to compute those with this when n is equal to, in this case, 180. So give me a pause, and then I will do it. Okay. Let's try pink. Smallest, right up there, upper left-hand corner. 0.07, so pretty close to 0. And then the largest, we did not get all the way up to 15. We got to 14.02. And actually, what am I doing? I got to give myself room because I want to put, ooh, that's quite a smear. I want to put the other 3 numbers in between here, of course. All right, so maybe about right here. Largest is 14.02. Okay, let's get the median. All right, the way you get a median is you go out and find that middle score. Since this is an even number, the middle data value, since this is an even number of data values, we're going to take the average of the middle 2, correct? With 180 data values, I got to go find the 90th and the 91st and take their mean. Okay, so if you look, I have 9 rows of 20 here. So if you start in the left-hand column, I got to go out to, what did you say, between 90 and 91. So the left-hand column is 20, and the next is 40, then 60, then 80. And I'm in then the 5th column, and I count down 10 more to get to 90, and that puts me at, I think, 5.92. And yeah, that's what I have. And what's the 91st one is 5.92 as well. So it's 5.92 plus 5.92 over 2, so it works out to be 5.92. Okay, let's get Q1. That's P sub 25. So I want to go out. So how do I compute this again? I want to go out basically 25% into the data set, right? So I take that 180 and I multiply by, if it's starting to come back to you, if you weren't able to do it before, you might want to pause me and see if you can get it now. I multiply it by 0.25, and if I do that, I will get 45. It's exactly an even integer, so I gotta go again between the 45th and the 46th number. So I go back to my organized data set here, and I go 20 in the first column, then 40, and then I go 1, 2, 3, 4, 5, and I get 3.7. So the 45th one is 3.7, and the next one is 3.72. So I have here 3.70 plus 3.72 divided by 2, and I get 3.71. Okay, you can see here now, if we're dealing with a bigger data set, if my way of doing it is, well, you got to take the 45th and the 46th and take their mean, you get this answer. If maybe your way of doing it is say, no, just get the 45th one, you'll get 3.70. Someone else may say, if you got the 45th one, jump to the next one, you get 3.72. With a large data set, you're getting about the same values, and that's usually true. It puts you at about the same place in the data set. So, as I said, there are different ways to compute these percentiles. And for a large data set, they kind of all don't really usually amount to much difference. But this is the way we're doing it, and so that's our answer so far. So we have the smallest here, the Q, that's Q1, didn't put that in. There's the median. Here's the largest. Let's get Q3. Got to go 75% into this 180-point data set. If you multiply 180 by 0.75, you get 135. So we got to go between 135 and 136, since 135 is an integer. So 135. So I start left. I go 20, 40, 60, 80, 100, 120. So I am in the 7th row. Right? And in fact, if I go to the bottom of, 7th column, if I go to the bottom, I'm at 140. So let me back off up 5, and I get to 7.95, and the one right after it is 7.96. So it's 7.95 plus 7.96 over 2, and I get 7.955. All right, so that went out to the nearest thousandth. Okay, well, I have now 5 numbers that I claim actually give us a decent way to view the data set. And rather than just start talking about these numbers, I'm going to just jump right in and do the box plot. So what is the box plot? Let's see here. Let me try this. I'm going to put a number line down here. Okay, I'm leaving a little space here because I want to write some more stuff. But here is my box plot. And like I said, it's also called a box and whisker diagram. So this is my number line. Okay? What I'm going to do is I'm going to put at the left end of it the lowest value, 0.07. I'll put at the right end of it the largest value, 14.02. I'm saying that all my data lay in between here. So that's one thing. I know here's my lower and upper limit. But how are the data spread apart? Are they all concentrated down here or down here? Are they evenly spread across? It's where these 3 numbers come in that we can actually get kind of a picture of that. So let's look at the median first. The median is 5.92. If I just thought, well, I'm going to think of this data as being evenly spread, this is almost 0, this is almost 14, so I would expect the median to be right at 7. Right? But it isn't. It's actually at 5.92. So that indicates that the data are a little bit more crunched this way than that way. So that tells you something. So, if I put 7 here, I'd be putting 5.92 maybe about right there. 5.92. Okay. Now what? Now let's do Q1, the 25th percentile or the first quartile. It's 3.71. And that's, I'm going to be rough here on the graph, but it, this is going to help me get a decent picture. 3.71 is about 2 below this 5.92, a little bit more than 2. So I'm going to say it's probably about right there. Okay. And might even be scrunched in a little more there, I don't know. And then Q3 is 7.955. It's almost 8. Right, so it's about 2 units above here, isn't it? Which should put you maybe about right there. 955. Should probably round that to 7.96, but that's, I'll leave it like that. Okay, I got those 3 points drawn, and then what we usually do, we turn this into, the reason it's called a box plot, is we draw a little box right above the first quartile, the median, and the third quartile. So we draw a little rectangle like this, up and over, and then I draw a vertical bar where I put the median. Next, because it's also called a box and whisker diagram, we draw little horizontal lines, we can call them whiskers, out to the lowest point and to the highest point. Okay. Now, looking at this image and seeing these numbers down here, it really does kind of give me a little bit of a picture of the data. I can say that what I have right here is roughly what we call the middle 50%. So even though I'm telling you that the data go from 0.07 to 14.02, I'm telling you that about half of it, the middle half, is between 3.71 and 7.955. So they're all kind of crunched in. There, middle 50%. The upper 25%, look, is all spread along here. It's between, really about 8 and about 14. There's almost like about 6 units here where I have about 25% of the points, the upper 25. And then here I have, not much more than 4 units. I get the middle 50%. And over here I have not quite 4 units to get the lower 25%. So it really does give me a nice image of the data. Let's see, I guess I want to say, so I want to point out down here, it's not necessarily evenly spaced along the number line. Along the number line. And I didn't give you a subject there. I just said not necessarily evenly spaced, and I'm talking about the different marks that we have here. If, like I said, for evenly spaced, you would expect the first quartile to be 1/4 of the way along the number line up from the lowest to the highest. You'd expect the median to be dead center, and you'd expect the third quartile to be 3/4 of the way along the number line. But that's not, of course, what these numbers represent. They represent, like for the third quartile, doesn't represent 75% of the distance from the lowest to the highest, but it represents the number where 75% of the data lie to its left. So this does tell you how concentrated the data are or spread apart they are at different parts. All right, so it does give you a nice image. One more thing, I guess. Let's see, I guess I'll define the interquartile range. Which is also called the IQR. And it's just, this is a definition, and it's just Q3 minus Q1. So here we get 7.955 minus 3.710, if you like. And that's what? 4.245. Okay, so the interquartile range tells us, again, how spread apart that middle 50% are. The whole 100% of the data are spread about almost 14 units apart, right? Almost. But that middle 50% is spread 4.245 units apart. All right. We'll